Hello everyone, this is session 21 for the mathematics course of basic third semester students of Nirvana. Here I am going to cover the topics lower and upper Riemann integrals and their properties. Let us recall the previous session, that is upper and lower sums. What was the definition for upper and lower sums? The sum m1 delta 1 plus m2 delta 2 plus m3 delta 3 plus mn delta n, which is equal to summation r is running from 1 to n mr, capital MR delta r. Their sum, which is nothing but your upper dot box sum, which is denoted by UPF, which is equal to summation r is running from 1 to n mr delta r. The second definition was for the lower dot box sums. So m1 capital Mn, here it is small m1 delta 1, like that we have del PF is equal to r is running from 1 to n mr small r into delta r. What is your oscillatory sum? If f is a mapping from AB, the interval AB to R, the set of real numbers, be a bounded function, and B be a partition. The initial point is A and the ending point is B, be a partition of AB. Let MR and small mr be respectively the supremum and infimum, and this is the rth interval. Then their difference, the UPF minus LPF, which is equal to capital MR minus small mr delta R, that is nothing but a oscillatory sum, and that is denoted by W of PF. Now we have the definition for lower and upper Riemann integrals. If f is a mapping from the interval AB to R, the set of real numbers, be a bounded function, then for every partition P belongs to P of AB, we have small m, that is infimum, small m is for infimum and capital M is for supremum. So m into P minus A. The difference is less than or equal to LPF, is less than or equal to APF, is less than or equal to the supremum multiplied by this P minus A, where the small m and capital M are the infimum and supremum of f on the closed interval AB. So for every P belongs to P of AB, we have L of PF is less than or equal to M of B minus A, and UPF is greater than or equal to small m into B minus A. The set LP of F, P belongs to P of AB, of all lower sums is bounded above by M into B minus A, and therefore it has a supremum. Also, the set UPFP belongs to P of AB of all upper sums. Here we have taken lower sums, now it is for upper sums, is bounded below. It was bounded above, it is bounded below, and it is M small m into B minus A, and thus it has an infimum. So for the first definition, if F is a mapping from AB to R, be bounded, and P of AB be a family of all partitions of AB, the lower Riemann integral of F on AB is defined as the supremum of all the lower sums, LPF, that is the lower bounds or the lower box sums for P belongs to P of AB and is denoted by integral from A bar to B f of x dx. That is for your lower Riemann integral. Now, here in the second definition, for the upper Riemann integral, what you have to replace? Here we have taken supremum, now we have to replace it by infimum. And for lower dot box sum is there, now it is upper dot box sums, and it is denoted by A to B bar, the integral A to B bar f of x dx. Now we have got the properties of Riemann integral. Theorem 7, if f is a mapping from AB to R is a bounded function, then always the lower Riemann integral is always less than or equal to the upper Riemann integral we have to prove now. So let us take two partitions P1 and P2, which belongs to P of AB. Then you know by the properties the lower LP1 of F is always less than or equal to UP2 of F, because no lower sum can exceed any upper sum. This is valid for each P1 belongs to P of AB. Keeping P2 fixed, the set LP1 of F, where P1 belongs to P of AB, has an upper bound UP2 of F, again by equation 1. Just call that by using equation 1. Also, the supremum of LP1 of F, if P1 belongs to P of AB, is always less than or equal to UP2 of F, because the supremum can be less than, supremum is always less than or equal to any upper bound. So the lower Riemann integral is always less than or equal to UP2 of F by the definition again. So call this as 2. This is valid for each P2 belongs to P of AB. Thus the set UP2 of F, where P2 belongs to P of AB, has a lower bound. So integral from a bar to b f of x dx from equation 2. Since infimum of up2 of f is always greater than or equal to the lower integral a bar to b f of x dx, because the infimum value is always greater than or equal to the lower bound. So, or the lower integral or the lower Riemann integral is always less than or equal to infimum of up2 of f. So the lower Riemann integral is always less than or equal to the upper Riemann integral. So always we can say that the lower integral cannot exceed the upper integral. So in a similar way, we have got theorem 8. If f is a mapping from AB to R is a bounded function, then we have to prove this inequality, where the small m and capital M are the infimum and supremum. So this value is always less than or equal to the lower Riemann integral, and which is less than or equal to the upper Riemann integral, and which is less than or equal to the supremum is multiplied by the difference of the um, elements here. Now we will prove it. Now we have m into b minus a is always less than or equal to, call this as the given equation, we will call it as equation 1 for every partition P belongs to P of AB. Since LPF is always less than or equal to supremum of LPF, where P belongs to P of AB, because any element cannot exceed the upper bound. So LPF is always less than or equal to this can be. This is nothing but the definition of your lower Riemann integral. So called this as 2 also, since UPF is always greater than or equal to infimum of LPF. Here we have taken LPF, here it is UPF. So here we are just using the definition of lower bound and upper bound here now. Therefore, UPF is always greater than or equal to the upper Riemann integral a to b bar f of x dx. This is by the definition of your upper Riemann integral, or integral from a to b bar, that is upper Riemann integral, is always less than or equal to this UPF. That is our equation 3. Further, we know that the lower Riemann integral is always less than or equal to the upper Riemann integral. This is by theorem 7. So calling this as your equation 4. From using these 4 equations, what we can write now, combining all the 4 equations, we can write m of p minus a is less than or equal to LP of f is less than or equal to the lower Riemann integral is less than or equal to the upper Riemann integral, which is less than or equal to UPF is less than or equal to m into b minus a, or else we can write m into b minus a is less than or equal to the lower Riemann integral, which is less than or equal to the upper Riemann integral, which is less than or equal to m into b minus a, just combining all the 4 equations. Now we have got note, first one, the lower sum is always smaller than the lower integral. See equation 2 here, this equation. Next, upper sum is greater than the upper integral. See equation 3 now here. Now we have got multiple choice questions. Lower sum is smaller than the lower integral. True or false? So it is true. Next we have second question. Upper sum is greater than the upper integral. That is also true. Next we have the third question. Lower integral cannot exceed upper integral. That is also true. Next we have, if f is a function from the interval ab to r is a bounded function, then what is the inequality? We have got the lower Riemann integral is always less than or equal to the upper Riemann integral. The last question, if f is a mapping from ab to r is a bounded function, then we have the inequality. See here, all in less than or equal to, it should come in the less than or equal to, there is a theorem 8 here now. So the first A is the answer for this question. So these are the references. Thank you for watching.